In the next section, we'll look at actually writing rate laws based off of some real concentration data. So in that first section, we looked at writing essentially general rate equations. So we looked at writing them in terms of the change in concentration of either our products or of our reactants over a set period of time. And even though we can express the concentration changes based on the reactants or on the products, in reality, they're really going to depend on the concentration of the reactants. So they won't really depend on the concentration of the products. Later on, we'll talk a little bit about Le Chatelier's principle, sort of towards the end of the chapter, and we'll talk about how products can sort of affect reaction rates, but for now, let's just look at this idea that it's going to be solely dependent on the concentration of the reactants. And we can make this general statement that the rate of a reaction will be proportional to the concentration of A raised to the power of m times the concentration of B raised to the power of n. Right? And this is the form that we call a rate law. So a rate law is a mathematical equation that shows the relationship of the reaction rate to the concentration of each reactant. So the relationship of the reaction rate to the concentration of the reactants. Okay, we write them in this form. So we say a rate is proportional to A to the m times B to the n. And here, we also need to include a constant. And this is called the rate constant. So we represent it as k, little k. So our rate law becomes rate is equal to the constant times A to the m times B to the n. And here, m and n are the reaction order. So m is the reaction order with respect to A, and n is the reaction order with respect to B. If I want to know the overall reaction order, I would say m plus n. So if they're both 1, the overall reaction order would be 2. So I could also ask you things like, what is the reaction order just of A? Or what is the reaction order with respect to A? And you would tell me whatever m is. If I asked you what it was with respect to B, you would tell me whatever n is. If I asked you the overall, you would say m plus n. Okay, but this is our general form of our rate law. So before, we were writing rate equations that were based on concentration or changes in concentration over time. Now we're writing the actual rate law with its associated constant and then the reaction orders. So how do we find this? Well, the values of the exponents, the value of our reaction orders, can't be determined so easily. So in our general rate equation, we use the stoichiometric coefficients to give us those fractions, so kind of give us that proportionality. But when we're talking about rate law, and we're talking about reaction order, we can't just determine it based on the stoichiometry. They have to actually be determined experimentally. So here's just a few rate equations. And remember, we're focused on our reactants. Okay, so we're not really concerned with our products. So if we take a look at this rate equation, we see that rate is equal to k, so k is again a constant, times the concentration of our reactant, so this methylated compound, brominated compound. Okay, we're leaving H2O out because that's going to be our solvent in this case. We'll get to that in a little bit. But it's just equal to a constant times the concentration of our main reactant, and then raised to the power of m. And here, m would be equal to 1. And if you notice, so it would go here, so if it's not there, it's a 1, our stoichiometric coefficient is also 1. But don't let that fool you. Okay, so if we take a look at this third equation down, so our rate order with respect to H plus is 2, but its stoichiometric coefficient is 6. For bromine, it's a 1, but its stoichiometric coefficient is a 5. So they may coincidentally line up, but don't let it fool you into thinking that it will always be equal to the stoichiometric coefficient. So in general, the exponents in the rate law are not the same as stoichiometric coefficients in the balanced chemical equation. So they may coincidentally be equal, but that's not necessarily the case. So here let's look at how to determine a rate law based on some experimental data. So here we have nitrous monoxide reacting with oxygen to give us nitrogen dioxide. Sorry, nitrogen monoxide, not nitrous monoxide. Nitrogen monoxide reacting with oxygen to give us nitrous dioxide, or nitrogen dioxide, excuse me. Okay, so NO plus O2 gives us NO2. And we have some experiments, 1 through 4. We have some concentrations. So here's a concentration for NO, here's a concentration for O2. Notice we don't care about our product. We're talking about concentrations. And then lastly, we have our initial rates. Okay, so we can use this data to actually determine M and N, our reaction order. Okay, assuming we know all of this information, we can determine our actual rate law, including the constant, based on this information. So how can we do this? Well, the first thing we want to do is we need to have a series of experiments where we've held the concentration of one reactant constant and changed the other. In this way, we know that the change in the reaction rate is due to changing that reactant. Okay, if we change them both, then we don't really know what's happening. We don't know what's having an effect on our reaction rate. It could be both, could be one, could be neither of them. Okay, so if we take a look at this data, we see a few things. So in this first set, so from 1 to 2, we see that our concentration of oxygen is unchanged. So we started from 0.015 in the first reaction, and our second reaction still 0.015. But what we've done is we've doubled the concentration of NO. Okay, and then in the second set of reactions, we've held, again, this reactant constant, and we've doubled this one again. So we kind of have two sets of data for that. But we also have, if we take a look, we have this and this are the same. So we have two reactions where we've held concentration of NO constant. We also have two more. And in the same sense, we've changed the concentration of oxygen. So let's just look at a single set of these at first. So let's look at the one where we're changing the concentration of NO. Again, holding the initial concentration of oxygen constant. And we can see what's happened to our reaction rate. So this is our initial reaction rate for these two reactions. Okay, we can set something up like this. So here we're trying to determine M. So we want to know the reaction order. So we write first our reaction equation, our reaction rate law. Okay, so we say rate is equal to K times NO to the power of M times O2 times to the power of N. And first we want to determine what is M. And we have to take a look at what's happened to our concentrations. So we know we're keeping oxygen constant, and we're doubling NO. Okay, so we're changing concentration of NO, keeping the concentration of O2 the same. So we can set this up. So 2 raised to the M. Okay, so saying that we've doubled the concentration of NO, and we're going to solve for M. So what goes on the other side of the equation? Where did the 4 come from? So if we look at our rate, we've actually quadrupled our rate, so times 4 in other words. Okay, so we can set up this equation. So we can say 2m, or 2 raised to the m, is equal to 4. Now what we have to do is we have to solve for m. So if we have 2 raised to the m is equal to 4, what value makes this true? Okay, of course, 2 squared will give us 4. That means that the value of m is equal to 2. If instead we had this, if we had, say, 2 raised to the m is equal to 2, what value of m makes this true? It would be 1. Okay, but that's not what happened. So our reaction rate quadrupled when we doubled the concentration of NO. So that means that m is equal to 1, so the reaction order with respect to NO is 2. So how do we find N? Well, with this set of data, we can do the same thing. So here we've held concentration of NO constant, but we've doubled concentration of O2. And then again, we can look at our reaction rate and see how it changed. So we can set up the same equation. So we'll say as the concentration of O2 doubles, so 2 raised to the n, so we're doubling the concentration raised to the n power, in other words, to find our reaction order. And then we look at what happened to our concentration. Well, it also doubled. Okay, so it was equal to 2. Okay, so as the concentration of O2 doubles, while holding the concentration of NO remains constant, while holding the same, the reaction rate doubles. So I have to solve this for n. So this is just what I just showed you. So 2 raised to the n is equal to 2. So what value of n makes this true? And of course the value would be 1. Okay, so the reaction order with respect to O2 would just be 1. Okay, this chart gives us some ideas about some values you may see. So we have 0 order, 1st order, 2nd order, and 3rd order. And generally, 3rd order reactions is about where we stop. Okay, so if I have a 0 order reaction, my rate law will look something like this. So rate will be equal to K times the concentration of A raised to 0. Okay, 0 meaning that it would just go to 1. No matter what the value is, raised to the power of 0 would be 1. So my rate is just equal to my constant for a 0 order reaction. What that tells us is that no matter what I do to the concentration of A, it won't change the rate of the reaction. So it doesn't matter if I have a lot of A or a little bit of A, the rate of consumption or the rate of the reaction will be the same. So my rate is just equal to my rate constant, which is K. If I have a 1st order reaction, my rate will be equal to K times the concentration of A to the 1st power. Meaning, whatever I do to the concentration of A, so if I double it, triple it, essentially I'm multiplying by that same value, by that same factor. Okay, and then 2nd order, 3rd order, obviously they're just squared or cubed. Okay, and so you may see things like this. So if 2 raised to the 0 is equal to 1, or 2 raised to the m is equal to 1, then we know it has to be 0. Okay, if 2 raised to the m is equal to 2, then it has to be 1. Okay, so you can kind of go through this for yourself, but it's just kind of showing you examples of some values you might see. So if 2 raised to the m is equal to 4, we know that it's 2nd order. Okay, so it works out like that. So you just have to solve those little small equations, solve for the exponent, okay, and that will give you the reaction order with respect to that reagent. Okay, so I can write the rate equation for this particular experiment, which we just found. Rate is equal to the constant times the concentration of NO squared times the concentration of oxygen raised to the 1st. So, with respect to nitrogen monoxide, the reaction order would be 2. So it's 2nd order with respect to NO. With respect to oxygen, it will be 1st order. That's because I have a 1. The overall reaction order would be third order. Because I have 2 plus 1 gives me 3. So that means the overall reaction is 3rd order. Okay, so I could ask you to solve for these individually, or I could just ask you the overall reaction order. But that's how we read this. But what if I want to solve for the value of K, my constant? So now I know my rate law. So I know rate is equal to a constant times concentration of NO squared times the concentration of oxygen. So based on the same data set, I can solve for K. Because if I look at my data, so let's just take experiment 1. I know rate, I know the concentration of NO, and I know the concentration of O2. So the only thing I don't know in this equation now is K. So I can select one experiment, rearrange my rate law to solve for K. Then all I have to do is take the values from the table. Okay, make sure they're in the same units, of course. Okay, and then divide the rate by the concentrations of the reactants with their respective orders. Okay, and then solve for K. Okay, so here I end up with a rate constant, 1.4 times 10 to the 4th and my unit 1 over meter squared, or molarity squared per second. Okay, so just choose one experiment, and I can choose the first experiment, the second experiment, the third experiment, or the fourth experiment, and I should end up with a K value that's nearly identical, if not identical. And generally speaking, you would do several experiments and take the average. Okay, but for any one particular reaction, it should be the same. Okay, so my new rate law, so my full rate law says that rate is equal to 1.4 times 10 to the fourth times the concentration of NO squared times the concentration of O2. So this, if you're asked to solve for a rate law, this is the full rate law. Okay, so including the constant and everything. That's your rate law. Okay, so remember where we came from. So we looked at the reactions where we held one concentration constant and we modified the other. And we looked at what happened to the rate. That told us the value of M and N. Okay, after that, we want to know what our constant is. So we select one experiment and then solve for K using the data from that experiment. Now with that, we have our K value, so we can write our complete rate law. So we just plug in our value of our constant and then keep the same orders that we found before, and that's our complete rate law. Okay, so let's take a look at how some of these may look. So if something is rate is equal to K. So suppose I wanted to know what the order was. Well, that's zero order. Why? Because I don't mention any of my reactants. Okay, so their order must be zero. What should my units be? So this is where it gets a little tricky, knowing what the units of K should be. But when you solve your equations, you should end up with the correct units for K. Okay, so if it's zero order, you might have molarity per second, or molarity times s to the minus 1. Okay, so remember that to the minus 1 is the same thing as putting something on the denominator. Okay, if it's first order, I may have just 1 over seconds. Okay, and these, remember, are the value for K. So essentially, we want to end up with a rate that's in molarity per second. So the value of K needs to cancel out the units so that we end up with that. And you can go through these on your own, but just understand, depending on first, second, third order, or zero order, the value of the units, the units of K will be different. Okay, so here's one for you guys to try, and it's just exactly what we just did. So it says the rate of the reaction between CO and NO2 was studied at 540 Kelvin, starting with various initial concentrations of CO and NO2, and it says the data below was collected. So I want you to determine the rate law and the value of the rate constant for this reaction. Okay, so this is just like the one we just worked out. So first determine your rate law, determine your rate and now determine your rate constant, or then determine your rate constant. Okay, so give this one a try. I know this is sort of a long process, but see how much you know with this problem, and then we'll go over it together. And that'll give you a good idea of how well you're understanding this so far. Okay, so let's take a look at this one. So we have a set of 5 experiments, and we have the initial concentrations for our 2 reactants, along with the initial rate for the reaction. And here they give it to us in molarity per hour. Okay, so we're looking to set up our rate equation. So let's first just write out our rate law. So we can say rate is equal to K times the concentration of CO raised to the M times the concentration of NO2 raised to the N. Okay, so that's our rate law. Now we just need to fill it in. So the first thing I like to do when trying to solve these, if you can, is to take each of the concentrations and the rate and divide them by the first one. So for instance, from here to here, dividing this would give me 1. From here to here, dividing the 7 by 3.5 would give me 2. So what that tells me is that moving from this line to this line, I've kept the concentration of carbon monoxide the same, and I've doubled the concentration of nitrogen dioxide. And I can do that for all the numbers, including the rates. And you end up with something like this. Okay? So this tells me that for this first 3 set of reactions, I didn't change the concentration of CO. Here I doubled it, here I tripled it. Here I doubled this concentration, here I cut it in half, here I kept it the same, and here I kept it the same. Okay? Over here, rate doubled, rate was cut in half, rate doubled, rate tripled. Okay, so it just gives you a faster way of comparing the numbers. If that's a little bit confusing, this step isn't necessary. What it would just mean is that you have to look at the numbers on your own and just sort of in your mind figure out, okay, this was doubled, this was tripled. So this just gives you a quick way of examining the numbers. Because remember, we're trying to solve for m, and we're trying to solve for n. That's the first thing we need to do. Okay, so with that in mind, we can forget about all of the actual data for right now. All we need is to know what happened to the concentration and what happened to the rate. So the first thing, let's solve for m. Okay, so I can say the concentration of CO raised to the m, or the change in concentration of CO raised to the m, is equal to the change in the rate. So let's find, so we're looking at CO. So let's find one of the reactions where we, let's say for this first one, it looks like we doubled it. So it's going to be from here to here. It's reaction 1 and 4. So if we go from 1 to 4, we've doubled it. So we're going to say 2, because we doubled it, so that's 2 times, raised to the m, okay, a reaction order. Now let's look at the rate. So from 1 to 5, what happened to the rate? It also doubled. Okay, so 2 raised to the m is equal to 2. So what power of 2 gives us 2? Of course, 1. Okay, so 2 raised to the 1 gives us 2. Okay, same thing for the last one. So the only other 2 reactions we can compare now are 1 and 5. Okay, so 1 and 5. So from 1 to 5, we tripled the concentration of CO. What happened to the rate? It also tripled. So we say 3 raised to the m is equal to 3. So m is equal to 1. So now we know the value of m is 1. So now we want to find n. So we'll do the same thing. So from reaction 1 to reaction 3, we cut the concentration of NO2 in half, and we kept the concentration of CO the same. And if we look at reaction 1 and 2, we kept the concentration of CO the same, but we doubled the concentration of NO2. So we can use those 2 reactions to determine m. So let's use 1 and 2. So from 1 to 2, we doubled the concentration of NO2, and we can look at what happened to our rate. Well, it also doubled. So from here to here we doubled, here to here we doubled. Okay, so 2 raised to the n is equal to 2. So the value of n is equal to 1. Here we cut our concentration in half. What happened to our rate? It also went down by 1/2. So 0.5 raised to the n is equal to 0.5. So again, n is equal to 1. Okay, so m is equal to 1, n is equal to 1. Our overall reaction order is 2. Okay. So now that we know the value of n and the value of n, we can write this rate law. So we can say the rate is equal to k times the concentration of CO raised to the 1 times the concentration of NO2 raised to the 1. And by convention, we leave off these 1s. I wrote them here for emphasis. Okay, so if there's no value there, you know it's a 1. So now we can solve for k. So rearrange the equation to solve for k. So divide both sides by the concentrations of the reactants. And then you'll get k is equal to the rate over the concentration of CO times the rate of the concentration of NO2. And then just pick an experiment. So here I picked the first experiment. Okay, so here's your rate. Goes here. And then CO and NO2. Okay, so CO and NO2. Okay, so just pick one experiment. Here I picked the first one. Plug those numbers in. Okay, after that, just solve the quick math, and that will give you a value of k. So here, the value of k is 1.9, and the units would be per molar per hour. And I kept those units the same just because that's what they gave us in the table. The question doesn't ask us for specific units, so I would leave them just like that. If it asks us per second, then we'd have to convert it. Okay, so that kind of just shows you where all the numbers came from. Okay, and then if we do this for any of these reactions 1 through 5, you end up with the exact same constant. So I went through and wrote these all out, but just to show you that you'll end up with the same rate constant no matter which reaction you choose or which experiment you choose. Okay, and then we can write our rate law. Rate is equal to K times CO times NO2. And our complete rate law would be rate is equal to 1.9, and then that's 1 over molarity hours times 3.8 times 10 to the minus 4 molarity times 6.5 times 10 to the minus 5 molarity raised to the first. So our rate will be equal to 4.7 times 10 to the minus 8. Okay, do we answer all of the questions? So it asks us to use the rate equation and the rate constant to determine the previous example determine the initial rate of the reaction. Oh, okay. So from here to here, I didn't really explain that very well. So here we know our reaction constant, we know our rate law, we know our reaction constant, our rate constant. So here it's asking us, okay, use that rate law you just found and determine the instantaneous rate for these two conditions. So we just bring in our rate equation. So now we know rate is equal to K times CO times NO2. So now you just plug in these numbers. So here's your concentration of CO, here's your concentration of NO2. Plug those in, and that will tell you the instantaneous rate for those concentrations. Okay, so for those conditions, rate is equal to 4.7 times 10 to the minus 8 molarity per hour. Okay, so let's take a look at this reaction. So the last line here, we have an overall reaction. So we say that 2 NO2 plus 2 hydrogen give us nitrogen and water. So this might be the reaction we would write. So nitrous dioxide reacting with hydrogen to give us nitrogen gas and water. Okay, but what's actually happening is this isn't just happening all in one step. Okay, so we have a couple of steps taking place. So steps can vary with reaction speed or reaction rate. So we can have steps like NO2 giving us N2O2, which might be very fast and reversible. And after that, we might have a step like N2O2 plus H2 give us N2O and water. And this step might be very slow. Okay? And then lastly, we have N2O plus H2 to give us N2 and H2O. This is a very fast step. And if I go through and I actually total up these equations, okay, so I can maybe write a plus sign here and combine all these, something like Hess's law almost. Okay. So cancel out everything that's equal. I end up with the overall reaction. Okay, but the point I'm trying to make here is that even though we can write a reaction with a very simple overall reaction, the rate is actually determined by the slowest step. Okay, so the rate for this equation, or the rate law for this series of equations, would be that the rate is equal to K2 times the concentration of N2O2 times the concentration of H2. Okay, so based on the slowest step. Okay, and this kind of chemistry can be used if you're, for instance, trying maybe to prove the mechanism or show some evidence for the mechanism of a reaction. You may break it down into some steps this way and then be able to show that, yes, this step must be the rate limiting step, is what we would call it. Okay, so the rate of this reaction is limited by the slowest step. Okay, and notice that it's actually governed by an intermediate. Why do we call this an intermediate? Well, because it doesn't actually appear in the final equation. So it appears for a brief moment in time, and then it's consumed. Okay, so we call that a reaction intermediate. But the entire rate of the reaction is governed by the step with the intermediate. Okay, so really the point here is just to say that the rate of a reaction, of any reaction, is governed by the slowest step, and we call that the rate determining step. Okay, so same thing here. So here we have NO2 combining with carbon monoxide to give us NO and CO2. Okay, and here we have a two-step reaction where, again, my reaction rate, my rate law, will be based on my slowest step. Okay, so here the rate will be based on this first step, which is the slow step, the rate determining step, and I can write a rate law that just says rate is equal to K1 times the concentration of NO2 squared. So the takeaway here is just to understand that the slowest step in a reaction determines its rate. In the next section, we'll look at integrated rate laws. So how do we come up with an integrated rate law, and what exactly is it used for? Well, first let's just start with the first order reaction. So we'd say that A, whatever A is, could be any reactant, goes to products. And for a first order reaction, we know that the rate is equal to K times the concentration of A. Okay, and I could rearrange this to say the rate, just using my general expression, rate is equal to the change in concentration of A over the change in time. Of course, that's negative. So therefore, I can sub in for rate that the concentration of A, or the change in the concentration of A over the change in time, is equal to K times A. So just setting those two quantities equal. Well, then I can use calculus to integrate. And from here, I come up with what's called an integrated rate law, where ln is, of course, the natural log. A naught, or A sub naught, is the initial concentration of A. A sub T is the concentration of A at some point in time during the course of the reaction. And that's all equal to minus KT. Okay, so in this form, this is known as the integrated rate law for a first order reaction. And what this allows us to do is it allows us to look at the concentration of our reactants over time. Okay, and based on this, we can figure out the order of a reaction based on some graphing methods. Okay, and here's the integration. So starting from the rate law all the way down to the integrated rate law. I won't burden you with this, but here it is in case you wanted to see it. But we end up with our integrated rate law, which is the natural log of A sub T over A sub naught is equal to minus KT. Okay, and we can rearrange this to be in the form of a y is equal to mx plus b equation, meaning we can graph it. Okay, so our first term, our natural log of A sub T is our y, minus KT, it's our m, T is our x, minus K is our m, T is our x, the natural log of A sub naught is our b. Okay, so the plot of a natural log of A sub T as y versus time as x yields a straight line plot with the slope of minus K. And that'll come into play again in just a few seconds. So just remember, if I have a first order equation or first order rate law, if I plot the data based on this equation, the slope should be a straight line and it should be equal to minus K. Yeah, I can do the same thing for a second order reaction. So I can say the rate is equal to K times A squared, easy enough. Then I can also say the rate is equal to minus delta A over delta T. So therefore I can do that same substitution, okay, and then integrate again in the same way. I end up with the same similar equation, so y is equal to mx plus b type equation, or I can actually use a plotting method again. And if I plot 1 of A sub T versus time, so 1 over A as my y, time as my x, this will yield a straight line with a slope of K. Okay, so great. What can this be used for? I mean, what do I really want to do with that? So this is what we can do with it. So if I have a set of data, so I have time and the concentration of A, I can make 3 plots. So this is a graphing method to determine the order of a reaction. So based on knowing that information, I can determine the order of a reaction using nothing but a set of time and concentration data. So here I just have 2A goes to B. And I want to know what is the rate of this reaction. So starting from just concentration and time data, first I'll take the natural log of A, and I'll take 1 over A. Because these are the three things I need to make my plots. So I need time, of course, but I also just need natural concentration of A, ln of A, and 1 over A. So for the first one, I'll plot just the concentration of A versus time, and I'll see what that plot looks like. Then I'll plot the natural log of A versus time, and lastly I'll plot 1 over A versus time. And if I would like to know what the reaction of this equation, or what the reaction order of this reaction is, what I want to do is look for the linear plot, or the most linear plot. In other words, look for the one that has a slope that's a straight line. And the one that is a straight line will tell me the reaction order. Okay, so from this information, I can determine that it's not zero order. Okay, so this is a curved line. It's not first order, I have a curved line. But I have a straight line for my second order. So this tells me that this reaction is second order with respect to A. And if I had a second reactant, I could maybe do a second set of experiments and determine concentration of my second reactant and do the same thing. Or I could do what we just learned before, where I'm holding the concentration of one constant and changing the other, and calculate the second reactant that way. But if I have this information, time and concentration data, then I can use this graphical method to determine the overall reaction order, or the reaction order with respect to that reactant, excuse me. Okay, so there's one of your labs where you're going to do this, so it's good that we're going over it. So it'll ask you to make some plots, or it'll give you some plots, and ask you to determine the reaction order. Okay, so this is what it's talking about. What about half-life? Okay, so it turns out half-life of a first-order reaction, I can say that T 1/2, in other words, the half-life time, is equal to 0.693 over K. Okay, so for a first-order reaction, the half-life is independent of the initial concentration, and each successive half-life is equal to a period of time. Okay, so every time we go through a half-life, half of the atoms have decayed. Okay, so if we start from T equal to 0, we have some set amount. So we have concentration of A. Okay, so we just have some initial concentration of A, and it falls from its initial value to A over 2 after one half-life, A over 4 for the second half-life, and then A over 8 for the third half-life. And it would just continue on that way, okay, essentially for infinity. Okay, so this is half-life. Okay, so the decay of a radioactive material follows first-order kinetics. So any radioactive material follows the decay follows first-order decay kinetics. Okay, so I can either determine the half-life of something, I can determine the decay constant, decay rate constant, things like this. So I can say that decay rate is equal to the change in the number of radioactive nuclei over the change in time, which is equal to K times the number of radioactive nuclei. So I can set up the equation. The natural log of n sub t over n sub naught is equal to minus kt. So just our integrated rate law for a first-order equation, or first-order reaction. And I can also say that T 1/2 is equal to 0.693 over K. And I can do this because if you solve out this natural log, what you end up with is this value. Okay, so we're talking about a half-life, so this is essentially 1/2. And if you're to take the natural log of 1/2, you'll end up with minus 0.693. So I can solve this equation to just be equal to that the half-life is equal to 0.693 over K. Okay, so based on that, let's see if we can solve this. So it says radioactive radion 222 from natural sources can seep into basements of homes. The half-life of this radion is 3.8 days. The question asks, if a basement has 4.0 times 10 to the 13 atoms of radion per liter of air, and the radion gas is trapped in the basement, how many atoms of radion will remain after 30 days? Okay, so based on these two equations, and based on the data given here, see if you can determine how much radion will be left after 30 days. Okay, so this one might be a little bit tricky. And to be honest, it's probably a little harder than a problem I would give you. But it's good to just know how to do this in case you ever need to, for some reason, calculate this. So let's just start out with what we know. So they told us our t1/2 is equal to 3.8 days. Okay. We know that our n sub 0, so our initial concentration, is equal to 4.0 times 10 to the 13 atoms per liter. Okay, and we know that our T will be 30 days. Okay, because I asked us after 30 days. And that's really all we know. So from this, we have to use the equations I just showed you. So we know that the natural log of n t over n, so this is our over n sub naught, is equal to minus k times t. And we know that k is equal to 0.693 over t. Okay, so how are we going to solve this? So what are we looking for? We're looking for n sub t. So n sub t is our question mark. We know our initial concentration, we know our time, and we can determine our constant. So how can we determine our constant? Well, just using our k equation, we know that k is equal to 0.693 over 3.8 days. Okay, so our k value will be 0.182 and days to the minus 1, or 1 over days, however you want to write it. Okay, so now I know my k value. So now I can use my natural log equation to solve for n sub t. Okay, so I'll just say that the natural log of n sub t over n sub naught is equal to minus kt. I know k, I know t, I know n sub naught, I can solve for kt. So let's plug in our numbers. Sorry, it's not wanting to listen to me right now. There we go. Okay, so we'll say the natural log of, we don't know n sub t, but we know n sub naught. So 4.0 times 10 to the 13th. I'm just going to write A per L. It's atoms per liter. It's equal to minus our K, 0.182 days to the minus 1. And that's times T, which is 3.8 days. I'm just going to put little d. Okay. So now this is just math, basically. So just trying to figure out I'm sorry, I put our t in wrong. That's why I paused for a second there. I wanted to make sure I was setting those up correctly, but we want to know after 30 days. Okay, so we'll put 30 days there, not a 3.8. So our 3.8 is our half-life. So we've already figured out our constant, so we don't need to use our half-life there. We need to use the actual amount of time. Okay, so now that we have this set up, now it's just solving the math. Okay, so the first thing I want to do is I want to get rid of that natural log. Okay, so I see the natural log and I don't want to deal with it. So first thing I'll do is I'll raise both sides, or raise e to the power of both sides. That'll cancel out our natural log. And if for some reason you can't remember that, if you look on your calculator, usually the second function is what undoes the first function. So if you look at your natural log key, you probably say e to the x. That will tell you that it will undo that. So this will cancel. So I'm left with n sub t over 4.0 times 10 to the 13 atoms per liter is equal to e raised to the, and if you multiply 0.182 times 30, you end up with minus 5.46. Okay, and that would be unitless since days and days cancel. Alright, this program is not wanting to let me do what I normally do. not trying to make you sick, I promise. Okay, so now we can just solve for m sub t. So first thing we'll do, multiply by 4.0 times 10 to the 13th on both sides. Okay, so this goes away. And we end up with, and on both sides, of course, so 4.0 times 10 to the 13th. Okay, so we end up with n sub t is equal to, and if we go ahead and take e raised to the minus 5.46, you end up with 0.00425 times 4 times 10 to the 13th. Okay, and so our n sub t will be equal to 1.7 times 10 to the 11 atoms per liter. Okay, that would be our final answer. So I'm going to try to zoom out. So see how it's chasing it away? It doesn't normally do that. Okay, that's about the best I can do right now. I think I need to clean my screen. Okay, so that is your solution for this radioactive decay problem. Okay, so last thing I'll leave you with in this video is just this chart letting you know the rate laws, their integrated rate equation, what plot should be the straight line, how you find the value of K, what the unit should be, and what the half-life equation would be for that order of reaction. Okay, so make sure you know all the important stuff from this because that will come in handy in solving this type of problems, especially which one should be the straight line, how should you find the slope, what should the integrated rate law. So if I just show you an integrated rate law, I would expect you to be able to know, okay, that's first order, something like that. Okay, so I will go ahead and I think we should break here. And when we come back, we'll go over some other things that affect rate.